Hi everyone, we're going to continue on to chapter 10 today. So remember that we are skipping through the chapter 9 notes. The chapter 9 notes are still going to be posted on Blackboard if you're interested in looking at them maybe over the summer if you're thinking about taking Organic 2 in the fall. When we look at the synthesis of alcohols, we've actually looked at quite a few different methods to synthesize alcohols. So let's go through the ones that we know as of now. So we looked at SN2 reactions. So remember SN2 reactions, when we have a primary or even a secondary carbon, they can proceed via SN2 reaction if we have a strong nucleophile. So our substrate here is going to be a primary. So in order to synthesize a alcohol, we can add a hydroxide. So remember bases with group 1 metals, something ionic like this. So we have sodium plus, OH minus. This would be a strong base, which would also be a strong nucleophile. So what's going to happen is we're going to have the iodide leave and the OH is going to come in. Remember, this is a one-step process. If this was a stereocenter, we would show stereochemistry with inversion of the stereochemistry. Another type of reaction that we looked at for the synthesis of alcohols is going to be the hydration of alkenes. So we looked at a couple different methods. We had the direct hydration, where we're adding water in the presence of an acid, something like sulfuric acid, and we're going to have Markovnikov and then that syn and anti-addition we would have. So remember our OH is going to go to the more substituted, again, just because this is Markovnikov addition. And again, we would have both syn and anti-addition. So it's not a selective reaction because remember it's proceeding via that planar carbocation. Another type of synthesis of alcohols that we have looked at already is going to be oxymercuration, demercuration. So remember, let's look at this alkene here. So again, this is going to be a two-step process. We use mercury acetate in water and THF. Our second step is our demercuration step, that sodium borohydride in the presence of a base, something like sodium hydroxide. So our mercury is going to go to the least substituted carbon. And then remember that in our second step, the mercury would be replaced with hydrogen. The OH would have the same stereochemistry. So that means we're going to have Markovnikov addition. And again, this second step here, remember mercury is being replaced with a hydrogen. So in this case, we're going to have Markovnikov addition again of our hydroxyl, and we can have both syn and anti-addition in this case. When we look at another type of reaction that we've talked about in chapter 8, so we had hydroboration, oxidation. So let's look at that same alkene. So remember in this case, what's going to happen is we have again a two-step process. We have borane hydride, and then we have hydrogen peroxide in THF sometimes with sodium hydroxide. So again, it just has to be basic. So what's going to happen here is we're going to have anti-Markovnikov. So anti-Markovnikov is going to mean that our hydroxyl is going to the least substituted. And again, this is anti. And what's going to happen here, I'll show stereochemistry to make it a little bit easier. So we have our anti-Markovnikov addition, and then we would have syn addition of our hydrogen. So we would also have the enantiomer that could form. So both the hydroxyl and the hydrogen could be wedges, and this methyl group here would be a dash. So remember that in this case, when we're looking at hydroboration oxidation, that borane, so that BH3 is going to go to the least substituted, and then OH is going to replace the borane in the second step, so that oxidation step. So if you're following the full notes or partial notes, you'll notice Number 3 on that first page is addition of acetylides to carbonyls and epoxides. So this is actually chapter 9, so don't be alarmed if you don't know what those reactions are, because you shouldn't really know what those reactions are because we didn't cover them. So don't worry about that. We're just going to kind of skip over number 3 on page 1. If we look at another synthesis of alcohols, so we looked at synthesis of 1,2-diols. So remember, this just means 2 hydroxyl groups. So if we look at this alkene that we've been using and we have periacetic acid in the presence of water, remember this would give us the trans 1,2-diol. So that means we would have one of our OHs as a dash and one of our OHs as a wedge. So this has to be anti-addition. And remember, it's anti-addition because we are forming that epoxide first with a periacetic acid. We can use also that MCPBA. So after the formation of our, epoxide, we are going to protonate this water. This bond is going to break right here as a water is coming in to attack. So again, since this one would be more substituted, it actually would break this bond right here, right? And water would come in here and attack, because water is going to want to attack the more substituted, just because, again, that has a greater positive charge. If there's one that's not more substituted, then it can attack either of the carbons. So this is going to, again, be anti-addition. If we look at the cis 1,2-diol, so when we look at cis 1,2-diol, we had osmium tetraoxide and NMO. What happens here is this is going to be a one-step process. In this one-step process, we have syn addition. So both of our hydroxyl groups are going to be added to the same face. So it can be either they're both going to be wedges, or they can both be dashes, either or. So now we're going to start getting into some new materials. So again, those are, you know already a lot of different ways to synthesize alcohols, but there's going to be a few different ways that we're going to talk about today. And what we really are going to be looking at is going to be Grignard reagents. So Grignard reagents are very common in organic chemistry. So Grignard reagents are going to be strongly basic, which is going to be important. And so they'll react with acidic protons. If we look at some common Grignard reagents, so very common Grignard reagents are going to be with magnesium metal. So when we have something with magnesium metal, something like this, the magnesium in this case is going to be our partial positive charge, right? Because it's more electropositive than carbon, which is going to put that negative charge onto carbon. So this a lot of times is kind of shown written like this. Grignard reagents, again, so this is just putting a large partial negative charge on that carbon atom. And that's why a lot of times you'll just see it written like this. So the formation of Grignard reagents is actually pretty straightforward. So what we take is we will take a alkyl halide, or a vinyl halide, or an aryl halide. So we need a halide in our starting material. So if we look at an alkyl halide, so something like this, what you're going to do is you're going to react magnesium metal. So when you see this little 0 up here, that's just indicating it's magnesium in the metallic state. And then we will use solvents like, so diethyl ether is shown as ET2O. Again, this is diethyl ether. So what we have is something that looks like this. And then THF is also a common solvent that's used for Grignard reagents. And we've talked about THF before in chapter 8. So remember, THF is tetrahydrofuran, and that is this chemical structure right here. So again, these are both very common solvents for Grignard reagents. And what happens is you're just adding the magnesium to your alkyl halide or whatever your starting material is. We can also have an aryl halide. So if we have something aromatic like this with, again, it will work with chlorine also. again, we'll just use diethyl ether. What's going to happen is we're going to have the formation of our Grignard reagent. So when I'm saying Grignard reagent, these are our Grignard reagents right here. Then we have also a vinyl halide. So we have something like this. Again, diethyl ether. So what we're going to form is something that looks like this. And again, right here would be our Grignard reagents. And then again, just remember when you're writing these reactions out, typical solvents that will be used are going to be ether solvents. So something like diethyl ether, which is right here, or that tetrahydrofuran, which is pretty commonly written as just THF. And the reason that we use these solvents is because that oxygen lone pair in both diethyl ether and THF helps stabilize the Grignard reagents. So when you have an oxygen, these solvents are called actually donor solvents because they have electrons to donate, and it helps solvate the metal in solution. We also have, so we talked about, right now we looked at basically magnesium Grignard reagents. We also have organolithium reagents, which again, these are really, really common in organic chemistry. So organolithium reagents are really the same idea. So what we have is we have something like this. So again, lithium's more electropositive than carbon, so it's putting a large partial negative charge on the carbon, which is going to be equal to this again. So very similar to Grignard reagents, we can form these organolithium reagents by treating them with an alkyl halide in the presence of lithium metal. So if we look at an example, if we take this alkyl halide here, we're going to react it with 2 equivalents of lithium. And a common solvent is actually going to be hexane for these reactions. So what happens is one of the lithium are going to replace this bromine here. And then the other lithium is going to kind of react with the bromine that's leaving. And it's going to form a salt, lithium bromide salt. So these lithium bromide salts typically are not very soluble. They're soluble, but there's some limitations with solubility in something like diethyl ether, which kind of helps to separate these types of reagents. When we look at why are we actually synthesizing these, right? So the importance of why we're using these types of reactions is going to be how we can synthesize alcohols in a different fashion. So let's look at some Grignard reagents and organolithium, and we're going to add them to carbonyls. We can form primary, secondary, or even tertiary alcohols depending on the specific carbonyl that we use. So let's look at our first example. So we have a primary we're going to take. So we have our halide right here. So remember when we're numbering them, that means it's a stepwise process. So first step is going to be basically forming our Grignard reagent. The second step is going to be taking formaldehyde, which is this compound right here. And then our third process is typically just shown with hydronium, just because we need some acidic conditions. So let me kind of walk you through this process slowly at first. So again, after the first step, what's going to happen is we're going to have the formation of our Grignard reagent. Once we have the formation of our Grignard reagent, what's going to happen is that this group right here is basically going to leave, and this carbon right here is going to attack this carbonyl. So when that happens, what we're going to do is we're going to have, so second step would look something like this. It will help to number, not on this one specifically because we only have 1 carbon, but as we're working through these, I will number the carbons just so it helps you. And what happens here is oxygen is going to lose that double bond. So oxygen will have a negative. So here's our carbon 1. We have oxygen coming off of it with a negative charge. Then we have a hydrogen and a hydrogen, exactly as it's shown here. So the reason that we need these acidic conditions is just to protonate that O-. So H+ or hydronium, however you would like to write it, what that's going to, oh, sorry about that. I have no idea what just happened. So what you're going to do is you're going to form a alcohol. When you add your H plus, again, that's just gonna protonate this oxygen right here. So let's look at another example. So another example, let's look at a secondary. So if we have something like this, and what we're gonna do is, so our first step again is gonna just be making that Grignard reagent. Second step, now we're gonna look at a little bit more complex carbonyl. Third step is just gonna be protonation, so hydronium or H plus you can write it as. So remember, after our first step, what we're gonna have is we're gonna have something that looks like this. This carbon here is going to attack at the carbonyl. So in this case, I recommend numbering because it can get a little bit confusing. So we'll say this is 1, 2, 3, 4, 5, 6, 7. So when this carbon attacks there, what we're going to be left with, so this is after step 2, is something, and remember these electrons are going to the oxygen to generate that O minus charge. So we have carbon 1, 2, 3, which is coming from here. Carbon 4 is coming from this position right here. So 4, 5, 6, 7. At carbon 4 right here, we have that O minus charge that we generated. And then we just have a hydrogen, this hydrogen right here. So when we put it in acidic conditions, what's going to happen is we're going to protonate that O minus, and what we would be left with is this product right here. So again, you don't have to show the hydrogen if you don't want to. You can also show it if you would like to. So let's look at another example. So these aren't too bad, but I really recommend, like I keep saying, numbering carbons. Otherwise, it can get really, really confusing when you are doing these reactions. And try to think of it stepwise. Don't look at it in a big picture. Look at it in small stepwise steps. So phenyl pH, it's typically abbreviated as, is equal to this aromatic system. So I'll use that for an abbreviation. You'll see that a lot in general in organic chemistry. So again, we have to form our Grignard reagent, the first step. Then we're gonna have the addition of this ketone, and then we need some acidic conditions. So we need the presence of H plus or hydronium. So first step, we're gonna form our Grignard reagent. And again, you can form magnesium bromide, you can form magnesium iodide, you can form magnesium chloride, any of those will work. You can also use the organolithium steps if you would like to do that instead. So it's the same thing, the Grignard reagents and the organolithium reagents will react in the same way. So this first step could also be lithium. So you would need 2 equivalents of lithium in hexane. But again, you can use this or this. All right, so we have the formation of our Grignard reagent. Now what's gonna happen is this is gonna leave. This carbon here is gonna go in here and attack. So let's number these, and it's gonna attack 1. So we have 3 different carbons here, but it's attacking carbon number 2, which is important. So when we number these here, we have carbon 2. Carbon 2 is attached to a methyl, which is, we'll say is 3 here. Another methyl, which is number 1. And then we're attached to this oxygen, which again is going to be O minus. So when we look at this, it's going to be in the presence of the acid. What's going to happen is we're just protonating this oxygen. So what we're going to be left with is this right here. If you're looking at the full notes, you'll see it written as this. Again, this pH is just equal to this aromatic system. So it's exactly the same. So let's look at a mechanism of maybe a more complex. So if we have more than 1 equivalent, for example. So if we look at a simple alkyl halide, so this time we're going to have it in the presence of 2 equivalents. So this means we'll have 2 equivalents of magnesium metal in the presence of diethyl ether. And then we're gonna have this ester right here. Again, we need acidic conditions. So H plus, So when we add our first equivalent of magnesium metal, what's going to happen is we're going to form magnesium bromide. What's going to happen here is this is going to again react with our ester from step 2. So this carbon here is coming in and attacking here. These electrons are going to the oxygen. What we're going to be left with, again, numbering may help. What we would be left with would be so we have carbon 1, 2, 3. So this carbon 4 is this carbon right here. So what we would have to do is we would have to, again, have some acetic. So when we're looking at this, what we learned when we were looking at, so this is going to be a little bit different than what we're doing because we have 2 equivalents. So when we were looking at substitution reactions or something like elimination reactions, we looked at this OET. So remember that's OCH2CH3. So this is a strong base. So it would act as a poor leaving group. But in this case, this is actually going to let us use this as a leaving group because this next step here is going to be very exothermic. So because this next step is very exothermic and we're able to form a carbonyl in the next step, the OET or the ethoxide group is capable of leaving. So when this group here leaves, this oxygen is going to go down here, those electrons, and form this ketone right here. So the initial product is going to be this ketone, but since we have another equivalent of magnesium bromide, right here, what we're going to do is we're actually going to add another equivalent of our starting Grignard reagent. And then when we add another starting equivalent of our starting Grignard reagent, again, this carbon here is now going to attack at this position. So what we would be left with is, so we're at, I don't know why it does that. So let's number. We have 1, 2, 3, 4. Here we have 1, 2, 3. So we're going to have carbons 1, 2, 3, 1, 2, 3. Carbon 3 is attached to carbon 4, which is right here. Carbon 4 has a methyl coming off of it. It has that O minus coming off of it. And then we have 3 additional carbons. So we have 1, 2, 3. So 4, 5. What we're going to do here is we would have, again, that H plus, and then that would give us OH. So again, this process is a little bit more confusing and in-depth just because, again, we had 2 equivalents of magnesium metal in this case, which was going to react with our alkyl halide a second time. So this is probably something that's not as common as all the other examples that we have looked at. So the confusing part again here is going to be down here when this ethoxide, so this is the ethoxide group, is leaving. It wants to leave just because in the next step we can reform that carbonyl. So carbonyls are usually more stable, so that's why that's kind of like the driving process towards that type of product. But this is definitely more complicated than something that you would have to know for the quiz. So all the other examples are something that you would be expected to know. Let's look at if we have the addition to an epoxide. So the addition to an epoxide, sorry, same idea. So this time I'll use actually lithium just to show you. But again, this could be magnesium in diethyl ether or magnesium in THF also. Our second step is going to be our epoxide. So remember, epoxide is this 3-membered ring with an oxygen in it. And then our third step would just be protonating or just acidic conditions, right? So let's number. We have 1, 2, 3. We have 4, 5. What's going to happen is same exact idea. So what's this carbon here is going to come in and attack this carbon here, and this bond right here is going to break. So when we have more complex epoxides, what's going to happen is they're actually going to undergo addition of the Grignard reagent at the less hindered carbon, as in like an SN2 reaction. So again, when you have an epoxide, what's going to happen is this carbon here is always going to attack the less substituted. So when we look at the product here, we're going to have 1, 2, so we have 1, 2, 3. It's attached to number 4. Carbon number 4 is attached to 5. Carbon 5 has the 2 methyl groups, and it's also going to have that OH coming off of it, right? When we look at another example, so let's look at this alkyl halide. This time we'll look at it with magnesium diethyl ether. Let's look at this epoxide here. So again, this part is the epoxide. We have acidic conditions. What's going to happen is we have this carbon here. So this carbon here is going to go on the back side, right, and attack, which makes sense because this is going to be a one-step process. So it's going to attack at the least substituted, which is going to be this carbon right here. So the product will look like, again, backside attack. Our OH is going to be our wedge. Our methyl would be our dash. So again, these have to be anti because of that backside attack. So I'm going to stop right here. In the next lecture, we'll just talk about some side reactions of Grignard reagents and organolithium reagents, just because, again, they are strongly basic. So it leads to some problems with other types of acidic compounds like alcohols, amines, and carboxylic acids. So we will talk about those, and then there's just a few different things that we'll look at with reduction of different carbonyls with different hydride reactants. And then that's really going to be it for chapter 10. So again, the quiz on the last quiz 5 that you guys will have is going to be on chapter 10 and chapter 11. But as you can see, there still is going to be substitution reactions kind of in there somehow and elimination reactions in there somehow. So kind of that first page of notes that we mentioned today, those are all reactions that you guys already know, and try to keep carrying on that information in your heads while you're working, and then just keep doing practice problems. So there are a lot of reactions. I completely understand that. The more comfortable you get with the reactions, the better you will do on the quiz. And again, this will all be carried over to Organic 2. So you'll need to know all these different syntheses for Organic 2 also. So please reach out to me with any questions, and I hope everyone has a great day.